This is a book review of Geometry by David A. Brannan, Matthew F. Esplen, Jeremy J. Gray. Copyright The Open University, 1999. I actually purchased this book because of the illustration on the cover, hoping to give me some clue as how to create or draw such a design. And luckily enough, there's quite a bit of information inside about it. But over time, this book has grown on me, and I think it was a wonderful pick at the time. Since I purchased it, I know there's a newer edition, which I have not updated mine to. I would like to start by looking quickly at the table of contents. Section 1, Conics. Section 2, Affine Geometry. Section 3, Projective Geometry, Lines. Section 4, Projective Geometry, Conics. Section 5, Inversive Geometry. Section 6, non-euclidean geometry. Section 7, spherical geometry. Section 8, the Kleinian view of geometry. This book has an abundance of illustrations, is nicely laid out, has problems and examples. Many of them worked out right on the page, and more have their answers in the back. And not just the answers, but a complete description of all the steps and worked out in detail of the many exercises from the book. So that's nice for home study. If you want to learn it, you can check your understanding by jumping to the back. It starts out, like it says, with conics, and of course does circles, ellipse, parabolas, hyperbolas, recognizing conics. And soon it gets right into using matrices. So it's not really very heavy with that, but it does use matrices as a way to deal with the conics, including the quadrics, the surfaces, recognizing quadric surfaces using matrices. Again, lots of worked out examples, lots of illustrations. And finally, we're into affine geometry, parallel projections. Again, there's some work with matrices again. You'll see over here that we're dealing with. And of course, affine geometry is very applicable now to computer science, and so seems more important than ever. Sieve's theorem, Menelaus theorem. Again, lots of nice illustrations throughout. A little bit of history at the beginning of every chapter tells a little bit about the history, in this case, of projective geometry. Drawing lines shows the medieval artist and their ways to draw in perspective. And so then it's off into perspective geometry. And as you can see, I like to mark up my books, so that's the way it goes. Desargues theorem, projective transformations. In fact, there's going to be a section on transformations in every chapter after this. So both the theory and also, again, with the matrices, exact formulas of how to compute these things or how to calculate. Second part of projective geometry is conics. I don't know how long this is going to last. Again, you can see there are just lots of nice illustrations, lots of nice worked out examples. Pascal's theorem, standard forms, Okay, inversive geometry. I really had fun with this chapter. Reflection and inversion. Reflection in a line and inversion in a circle, which kind of gets me a little bit closer to that picture on the cover. Yes, when we get to here, I guess I had it marked too. Extending the plane, and now we're going to do transformations of the complex plane. And so at this point, he introduces complex numbers and shows how you can think of inversion in circles and lines using complex numbers. And here we get our friend the Mobius transform. Matrix representation of the Mobius transform, again using complex numbers. how you can compose them, do one after the other. Apollonian circle theorem. What fun. Families of circles, coaxial circles. Chapter 6, non-Euclidean geometry. And as I do these book reviews, you're going to see that that's really kind of what I've been drawn to learn about is non-Euclidean geometry. And I'll go through this one now. What is non-Euclidean? In this case, he's going to use the Poincaré disk model. Other books on non-Euclidean geometry use other models or start with other models, but I like this one. This is nice, and again, it kind of builds on that inversion in a circle from the preceding chapter. Transformation, again, now we can use the Mobius transform in the non-Euclidean Poincaré plane. Distance in non-Euclidean geometry, again within this disk model. In other models, distance is calculated a little differently. Non-Euclidean midpoints, non-Euclidean circles. Non-Euclidean triangles, hyperbolic triangles in the Poincaré disk. Talks about them, and lo and behold, there's my my favorite picture with a pretty good description on how to calculate them and understand them. He kind of works through it. Right-angled triangles, he calls them D triangles, disk triangles in the disk. Again, there's lots of math, but it's really quite straightforward. Basic trigonometry. I don't think there's any calculus in here. This doesn't go into the differential geometry. Tessellations, oh, aren't those pretty? This one, of course, is the famous picture by M.C. Escher, and showing how it's made of reflecting these D triangles, he calls them, or hyperbolic triangles. And here's just one page or 2 pages on an alternative model called the half-plane model of non-Euclidean geometry. Off into Chapter 7, spherical geometry, spherical triangles, area of a triangle, dual triangles, distance between 2 points, spherical trigonometry, which is interesting, the Kleinian view of geometry. And so in geometry and Kleinian's view, we want to look at invariance. So we look at the transformations that you can do within that geometry and then study the invariance of those transformations. And we're kind of at the end of the main. Here's like Appendix 1, primer of group theory, primer of vectors and space vectors, and then solutions, which again goes on, lots of nice worked out solutions to get you started in geometry and kind of get the basic lay of the land. If you don't know this stuff, if you're interested in geometry, I don't know of a better place to start. Again, assuming you had high school geometry, then this is a good second course, I do believe. Thank you for listening.